in immersed drilling of the past decades. Innovations that have stretched the limits and that have increased the competitiveness of the immersed tunnel technique. And you will find the try to go to the next slide, which seems difficult. Can you see the slide still?
Hans, maybe can you try to share your screen again?
I will.
Yep. You try to close it and then share it again and see whether we can solve the problem. Okay, looks like it's working now.
Okay, thanks. So in this slide you can find the contents of my presentation. Start with a general introduction of the tunnel technique, which may be useful for people not so familiar with the technique. Then I'm going to describe a number of innovations that have pushed the boundaries of the feasibility and opportunities for immersed tunnels. And I will close with some interesting specials, project cases that includes the longest immersed tube tunnel in the world that is now under preparation for construction. And if you like, one of the shortest immersed tunnels in the world, the Amsterdam North-South Line metro tunnel under the central station, which is only 100 meters long. In this slide, I'm going to share with you some information about the past. Immersed tunnel techniques can be regarded as a very mature immersed tunnel technique, and over 150 tunnels have been built around the world for road, rail, and utilities. The first tunnel was being constructed in the USA and more than 100 years ago under the Detroit River. And they are, let's say, the starters of the immersed tunnel technique. It took a number of years before the technique was transferred to other parts of the world, to Europe, for the Maas Tunnel in Rotterdam in the late 30s and the early 40s. And the same goes for Asia. The first tunnel was being constructed under the Eiji River Tunnel, Eiji River in Osaka, Japan. In this slide, you see the basic principle of immersed tunnel, how it's being used traditionally. So you can see the cast and basin layout where precast segments are being constructed and in a location remote from the project location. In this cast and basin, the tunnel elements can have lengths of around 100 to 200 meters. That depends on the project and on the sizes of the cast and basin. And they will be closed off at one point to make it suitable for flotation. So you create some sort of a shoebox that is capable of flotation as soon as the cast and basin is flooded. After the being flooded, the tunnel can be transported to the project location and being immersed into position using big floaters, the pontoons, and a water ballast system that gives you the capability to control the buoyancy weight ratio of the element. Actually, the basic principle of the immersed tunnel technique is that the tunnel has to be able to be afloat while being transported and immersed into position. And in that respect, it has to have a suitable factor of safety against sinking. But in the final stage, it has to have an adequate factor of safety against uplift. And that goes for both for the construction stage and the final stage. And moreover, the tunnel structure has to meet the design codes in terms of strength and durability. So you can see on the right figure the main components of the immersed tube cross-section, which means the airspace being determined by the traffic envelope, room for installations, rooms for evacuation and safety. You have another component, which is the structural concrete. Those two components, they determine the flotation behavior of the tunnel. And the third component, the ballast concrete or the ballast water component during construction stage, has to with that component you control the factor the safety against uplift during construction and also during the final stage. There are some potential advantages for immersed tunnels, and this is especially the case in river crossings, or traditionally the case in river crossings, but it becomes more prominent also for other types of crossings, as I will explain later. In this slide, you can see why immersed tunnels can be quite competitive if you compare them to bore tunnels and bridges. So, as you can see on the illustration, for a typical river crossing, an immersed tube tunnel can be located immediately underneath the riverbed or under the seabed, which which result in relatively short approach tunnels on the riverbanks, cut and cover tunnels. If you compare that with a bore tunnel that from a buoyancy point of view is generally located on a deeper level, the approaches will be deeper and longer generally. And that also goes for a bridge that, when located in port areas with high air clearances may be involved, the approaches becomes even longer. This is an example of a very high bridge, and you can also see the impact on the urban environment of the approach bridges. If you would go for a low-level bridge, then especially in port areas, you can see the impact on shipping, but also if it involves a motorway, you can see the obstruction that it also means for the road traffic. The photo presents an example in the Netherlands where the movable bridge was replaced by an immersed tube tunnel. But also when it comes to bore tunnels, you can see how the deeper level of a bore tunnel, twin tunnels or a two-stack tunnel can increase the length of the approaches and thereby also the associated costs. And in this slide, you see the example of the Neva crossing in St. Petersburg in Russia. It's a case study. The tunnel was not built to date. It's not built to date. Practically every shape can be covered by an immersed tube tunnel. It's rectangular, circular. You can see on the slide the kind of immersed tunnel projects and cross sections that have been realized so far. And in the lower part of the slide, you can also see how cost-effective immersed tunnels can be for wide tunnels. So that means multiple lanes or a combination of road and rail traffic, resulting in wide tunnel sections. In the immersed tube tunnel cross section, you can accommodate all the various traffic modalities, and if you would do that with a bore tunnel, you can see that it would result in multiple bores or very big bores that make the immersed tunnel technology quite competitive. And it can be used in various waterways that will be illustrated later, but it can be used for very shallow sections, for very shallow waters, but also for under buildings or for very long sections for the 20-kilometer fixed link between Germany and Denmark, for instance. So summarizing the advantages and the characteristics of immersed tunnels, it's suitable for various and relatively poor soil conditions, and the reason for that is that the tunnel weight is generally less than the soil weight that it replaces. So the ultimate soil pressure will be less than the original soil pressure. You can have parallel construction processes. So the tunnel element construction can be done in parallel with the dredging and in parallel with the approach ramp construction. There's a relatively low and manageable risk profile. For instance, uncertainties in soil in the underground can be discovered on a really early moment in the project. For instance, obstacles that were not detected during the survey can be detected while doing the dredging operations prior to the immersed tunnel installation. And the tunnel can be suited out for dealing with severe seismic events, has been demonstrated by the many immersed tunnels that have been constructed in Japan, tunnels that have been constructed in Turkey, tunnels that have been constructed on the west coast of the US. These are all quite sensitive seismic areas. And what is regarded as a serious advantage as well is that 80 to 90% of all the design and construction works can be done by local companies. So there's only a limited input required from international specialists, consultants or subcontractors, which makes it quite attractive for the local construction industry. But obviously there are also disadvantages, or maybe prejudices if you like. And that's the environmental impact of dredging. This is regarded could be regarded as a disadvantage, especially when contaminated soils are involved. Especially dredging requirements could solve part of the job, but in case contaminated soils are involved, then you should take account for higher disposal costs. But it's also sometimes rejected for the wrong reason or without detailed study. It never compares, or hardly ever compares, the impact of the actual dredging operations for the immersed tunnel in comparison to annual maintenance dredging in ports areas or something like that. And there are also opportunities for the because with the dredged material, land reclamations can be realized as well. Construction impact on shipping is also a point of concern. There is impact, limited but manageable. Dredging and immersion and backfilling operations will have an effect on the waterway. But in practice, this issue is often addressed by properly and good communication with authorities, port authorities or municipalities, if you like. I'll give you now some examples of the developments that have been realized over the years, over the past decades, and that have pushed the boundaries and also increased the opportunities for immersed tunneling. Traditionally, the tunnel elements are constructed remote from the project location, but generally within a certain distance. And since the last decades, you see that the Karsten basin locations become more the availability becomes more of an issue, and the transport distances have increased. But as you can see, there are many examples. There are examples of tunnels that have been constructed on a great distance and that have been transported over sea in offshore conditions, and have managed to come from the construction location to the final location. This is followed by not only transport but also immersion of the tunnel elements, which becomes more delicate because of the more adverse offshore conditions, especially when it comes to swell waves that can have an impact on the immersion operation and makes it more delicate. So apart from the heavier equipment that is required to do offshore immersion, also these kind of features need to be addressed. And sometimes in the more challenging circumstances, additional or special equipment has been developed to manage and control the more advanced weather conditions and wave conditions. This is an example of an external positioning system that has been developed for the Busan-Gyeonggi link, and that allows the final and accurate adjustment of the positioning of the element under these adverse conditions. This is an example that you may have seen this morning already in the presentation about the Hong Kong-Zhuhai-Macau bridge link. This is an innovation that has been implemented in this project, and that involves the special installation of the closer joint, which is the final piece of the immersed tube tunnel, which would take approximately 3 months using traditional methods, but 3 months is a bit long in adverse marine conditions. And with this concept, installation could be done within a day, which makes the sensitivity in relation to the marine conditions a lot less. One of the latest developments is also quite close to where you are at the moment. It's a special transportation and immersion vessel, self-propelled, that is used for the Shenzhen link in China. And that means that you can do without a lot of tug and push boats to bring the element from the transportation, from the construction site to the project location. Then when it comes to soft and variable ground conditions, so the immersed tunnels have been applied can be applied in relatively poor soil conditions without additional measures. However, in the past, if really poor soil conditions were involved, risks were often mitigated by the use of expensive pilot foundations, which is now being considered only appropriate for the smaller links. So if you would have to do that for the very long sea straits, then it will become quite expensive. So in-depth and advanced geotechnical design strategy have resulted in a more economical design solutions. For instance, soil treatment that can be used on a larger scale and suitable for long sea straits. And this would be appropriate, especially in case of variable ground conditions or variable load conditions, which could improve the ground properties, but also the uniformity of the geotechnical profile. So you would have a double effect. But also advanced geotechnical analysis combined with the observational method could demonstrate that even in soft soil conditions, the direct foundation of tunnel elements would be feasible. The selection of projects that have been used large-scale soil treatment is, for instance, one of the examples is, for instance, the Busan-Gyeonggi link, where the large-scale cement deep mixing were used to manage the unsure properties of the marine clay, and especially in combination with the heavy locking fill and backfill that had to be used for seismic purposes and for the high wave conditions. Also, sand compaction piles were used in an area where the tunnel protruded above the seabed, and where the sand compaction pile was combined with preloading. Hong Kong Shanghai Macau Bridge Link has applied quite some innovations as well in terms of large scale sand compaction piles around the islands and in the transition area from the islands to the immersed tube tunnel section, where fit for purpose and tailor-made sand compaction pile concepts were used, probably also described this morning. This is an example in Europe, the Marion Tunnel in Gothenburg, where up to 100-meter thick clay layers were encountered, but they were quite uniform. So for this project, it was decided that direct foundation on the thick clay layer was feasible, and using the observation method, monitoring, taking account for settlement reservation in the traffic envelope, was made it possible to have a direct foundation of the tunnel on these clay layers. Then, regarding the dredging and environmental issues, immersed tunnels are sometimes rejected for not the right reason and without too much detailed studies. And it has been noted that in some projects the bore tunnel was selected over the immersed tunnel just because of the sensitivity of environmental impact of the dredging, but without any quantification, and without considering the wider perspective. As I already mentioned, annual maintenance dredging in port areas is generally much larger in volumes. So there's much to gain in costs and in integration of the tunnel in the area in case the immersed tunnel will remain in competition and is not rejected for the wrong reasons. So there are obviously locations where bore tunnels are much better solutions, but it's important also for clients in terms of cost and quality to have as much competition as possible. For the ITA, there is a paper developed which gives you more details on immersed tunnels in the natural environment, which is also discussing some case studies regarding dredging and environmental issues. So where relevant and important impact of dredging can be limited, for instance, by special dredging equipment, in using more mechanical dredging instead of hydraulic dredging. In case contaminated soils are involved, you could use special equipment, closed clamshells or adaptive auger head dredgers that can really mitigate the effect of spillage in the water in the project location while dredging. But also other measures can be taken. On the slide you can see the Björvika tunnel, which is a tunnel that has been realized in a port area where there was serious pollution. In this project, dredging curtains, in this project, silt curtains and bubble screens were used to contain the polluted sediments, but it can also be used to the limitation of dredging in certain periods of time. For instance, when dredging is regarded to be adverse for the fish migration. So in that respect, you can also mitigate effects of dredging also in good soils by the limitation of the dredging in certain periods of time. For instance, in the new time crossing. For the new time crossing, large-scale monitoring of the water quality was also being applied prior to almost a year prior to the dredging operations, but also during the dredging operations. And the quality was measured by looking after the dissolved oxygen levels, turbidity, current velocities, and sediment contaminants. For the big sea straits, also monitoring programs have been developed to monitor the water quality during and prior to the dredging operations, and to take action in case levels are being exceeded. This is an example of the opportunities that can also be connected to the technology. So the dredge material that is coming from the trench has been used for the land reclamations or for artificial islands. In the slide, you can see the example of the Öresund link, where a 4-kilometer artificial island was created from the dredge material from the trench, and the artificial island was in transition between the bridge and the tunnel section of the link. But also for the Fehmarnbelt link, you can see the dotted red line, which is representing the current coastline, and you can see the land reclamation that is being achieved by the use of the reuse of dredge material. Then the production of tunnel elements. Also in the production of tunnel elements have been some interesting innovations. On this slide, you can see the traditional ways of constructing tunnel elements in the casting basins or on slipways in shipyards, especially used for steel tunnels, in ship docks where you can build elements, sometimes combined with floating casting, because the rent of a ship dock can be quite expensive. So you could split up the construction of the tunnel elements. And on the right bottom side, you can see the inline construction of tunnel elements. So the tunnel elements are being constructed in the alignment in one of the approaches of the tunnel. For the long tunnels, the tunnels crossing sea straits, factory method has been developed using the cast and launch method. This is being used for the Öresund link, for the Hong Kong-Shanghai Macau bridge link, and is now also being used for the Fehmarnbelt link, being prepared for the Fehmarnbelt link, and also used, by the way, for the Shenzhen tunnel in the same location as used for the Hong Kong-Shanghai Macau bridge link. That means that that a factory method has been developed where the rebar is being prefabricated and shifted into a location where concreting can take place, concreting of the various sections, which are being pushed into a shallow part of the basin, and after the element is being completed, or the two elements have been completed, a sliding gate can be closed. And the dog gate can be positioned into the entrance to the water. The area in the casting basin the water level can be raised, and the tunnel elements can be floated up. transported to the deep part of the basin and then be taken out to the project location after the dock gate has been removed again. Also, the submersible barge technique has been tried out in Guangzhou for the Luntao tunnel, where the tunnels have been constructed on a ship, have been transported to the location, and in a deep dredged pocket, the tunnel element is offloaded from the barge, floated by itself, and immersed into position. This concept has been studied as well for the femur belt link as an optioneering in an optioneering exercise, where the factory method has been combined with a submersible barge. So the tunnels are being constructed in following the same method as I just described for the cast and launch facility, then pushed out and then pushed on to a submersible barge that will take the tunnel to the project location, and in a deep pocket the tunnel element will be offloaded and floated by itself and immersed into position finally. Another example of an innovation is the parallel construction in the tunnel approach. So I presented in one of the previous slides the parallel construction of the construction of the tunnel elements in one of the approaches. The downside of this method is that the cut and cover tunnels cannot be constructed at the same time. With this method presented on this slide, parallel construction can still take place. So the tunnel elements are constructed in the two approaches, and at the same time the cut and cover tunnels are being constructed. After the tunnels are finished, cut and cover tunnels and the tunnel elements will be taken out and immersed into position. So in the cross section on the right bottom, you can see an indication on how that looks like. So the immersed tunnel element is on the top on the temporary floor. But also underneath, also the technique is used for special locations underneath buildings. I will come to that a bit later in detail, but also underneath runways. So in the example, approximately 500 meters of immersed tunnel has been used to cross one of the runways on Schiphol Airport in a very quick way, which is important to limit the downtime of a runway. Structure concepts that have been developed over the years to deal with special circumstances. Structure concepts, for instance, the Shenzong link, where the 4-lane, 2x4 lane road traffic would result in very, very heavy concrete size dimensions, and that is now being accommodated with a full sandwich steel concrete tunnel. But also for in case you have to pass very shallow waters or narrow waters, you could use different concepts, steel concrete combinations that have been used for the surface tram tunnel, for instance, and to some extent also for the Marmaray crossing, where in a shallow dock the first stage of the construction was carried out. Concrete slab and the lower part of the walls were constructed. The walls were still covered by steel sheets. Then the elements were taken to deeper water and finished at one of the jetties in the same port area. Then I will share some of the project cases and I will start with the femur belt link, which is being prepared for construction, or actually have started construction already, where it comes to the marine works, the dredging and reclamation works. It's a tunnel that is being planned between Puttgarten and Rotbyhaven. Puttgarten in Germany and Rotbyhaven in Denmark. The link is approximately 20 kilometers, and it contains an 80-kilometer immersed section. These very long links, they have their own challenges, and that are related to these exceptional lengths. So it's important to have focus on items like optimization of the cross-section, because if you can save costs for 1 meter, you can save them on the full 80 kilometers. Also, the efficiency of the production of tunnel elements and the development of a suitable state-of-the-art safety concept can make a difference in whether you would select an immersed tube tunnel or a bridge solution. Actually, I'm going to describe the challenges I just described, the items that are relevant for that, and also compare it on the end of this case study with the results of the competition that was being held in Denmark between the tunnel solution and the bridge solution, which was in fact a very good way of getting the best out of both options. In this slide, you see the cross-section of the standard cross-section of the tunnel. The standard tunnel elements have lengths of approximately 42 meters in width, 9 meters in height, and approximately 217 meters. It contains 2 sections of 2 tubes for traffic, 2 tubes for rail, and a service cell between the 2 traffic tubes. The cross-section could be optimized because with the introduction of special elements, it was possible to optimize the space that would be needed for M&E equipment in the tunnel. So by collecting all the transformers and other equipment in the special elements, the standard elements could be optimized with regard to this space. And that resulted in special elements that have 2 stories, that an upper story where the traffic is running, and a lower story where the M&E equipment is being stored. In the elements, there was also room for a parking base where maintenance people could have easy access to the spaces below the road and traffic levels, which also was quite beneficial to the maintenance of the tunnel. Then the efficiency of the production of the tunnel elements. For this project, the Öresund link that was being realized in the late 90s, the Öresund link was used as a reference, and that also goes for the production yards of the elements. So in this slide, you can see photos of the Öresund link that included 2 production lines for approximately 3.3 kilometer of tunnel, and that meant that if you would have the requirement to achieve a similar construction time, that you have to increase the number of production lines. So in this slide, you can see the client reference design with 8 production lines for the tunnel elements for 20 kilometers for the 20 kilometer tunnel, and 1 production line for the special elements. And this was in one of the previous slides. You could see the submersible barge technique that was also being studied for the same project. In the final solution that is now being prepared by the DNC contractor, the successful DNC contractor, the number of lines is further optimized. Safety concept was quite essential for this project, because the exceptional length required a state-of-the-art and tailor-made solution for the tunnel. Safety and self-rescue becomes more prominent once the tunnel length increases, and measures can be taken to make the tunnel safer than an open road. You have at least more constant conditions in a tunnel than on an open road. However, you also have to take care of, and that's actually level one, make it as safe as possible, prevent the prevention of accidents and fires through measures in the design, which means robust concrete structures, suitable escape cells, traffic information systems, and special lighting systems. So you can see it on the second image. These are moving images on the wall that will keep the awareness of the driver to as good as possible. You can make the road safer, and you can make the road in the tunnel safer than in an open road, but once an accident happens, the consequences may be more serious. So it's important to control the incidents as much as possible and to implement measures as much as possible for the self-rescue of the people, which is level 2, and that included closely spaced escape systems, exit signage, emergency stations, incident control, also a water-the-loose system to control the fire. And there is a level 3, which means the facilities for emergency services, response and rescue. Important is to be aware of the fact that for such a long link, it takes time before the emergency services arrive at the scene, which means that for that reason, self-rescue on level 2 is so essential. But for this link, also a dedicated fire brigade will be implemented to keep the tunnel as safe as possible and to respond as quick as possible to any event that can take place. This gives you an indication of the kind of devices that have been included in the tunnel.
Sorry to interrupt, Hans. We have over quite a bit. Can you try to wrap up maybe within 2 or 3 minutes?
Yeah, I will try. Important for the safety concept is obviously the ventilation design. For this tunnel, a longitudinal ventilation has been implemented as a normally self-ventilated tunnel by the piston effect is already doing most of the job. But the ventilation system is also being used for the normal operation, the maintenance, and the emergency. So it is relying on the principle that the tunnel is not located in an urban area, so will probably the traffic that is ahead of the fire can leave the tunnel without obstructions. Many scenarios have been studied also for 2 accidents in the tunnel, and that has been assessed as a very low risk, and that means that in terms of ventilation, you could do without a ventilation island. You could do without a separate ventilation duct, and you do not need any provisions at the portal, which is another reason why you could very much optimize the cross-section. Moreover, the reuse of dredge material by creating land reclamations was also reducing the length of the tunnel. So why was an immersed tunnel preferred over a bridge for the Fehmarn Belt link? The costs were more or less similar. There was not too much difference in cost, but the availability of the tunnel was regarded much larger during, for instance, adverse weather conditions, and by implementing the state-of-art maintenance facilities in the special elements. There was less hydraulic impact, less visual and environmental impact, which was regarded very important by the environmental people, and the involvement of local contractors was better organized with the immersed tube tunnel. For the bore tunnel, costs were higher for the bore tunnel, and that was determined for main part by the higher M&E costs that had to be split up in various tunnels, maintenance and availability, construction risks, and the operational safety. For this project, I will only flip through very quickly to give you an impression on what has been done for the immersed tunnel under an historic building in Amsterdam. But for the sake of time, I will only give you a very brief impression. This is the location where the station, central railway station, north-south oriented, and the metro line north-south, east-west oriented, and the metro line north-south oriented. This gives you an indication of the structures that has to be repaired with the immersed tunnel underneath the central railway station. Advanced a canal was being created underneath the central railway station using state-of-the-art building pit concepts. And once these were in place, the tunnel elements could be taken in. I will give you an impression on how that went, because there was a very low headroom. This is the red dotted line is the level, the bottom face of the structures. And the original water table, the normal water table, is just below that, 40 centimeters. So there was a very little room to get the tunnel shifted underneath. And therefore, a locking pit was being created, which you can see on the two photos. And tunnel was being introduced in the lock pit being closed off. That's the left bottom picture where you can see that the tunnel is almost in. Then it is shifted underneath until an intermediate prop level. It has been taken down a bit, and then it is being immersed into position. You can see it here in a different way. The tunnel element with the two obstacles. Obstacle one underneath the old station building, and obstacles also in the entrance part. Tunnel is being taken in up to the strut levels. Pontoons are mounted on. Water tables are being lowered to -3. That's the level you could see on one of the first slides in this case study. And then the tunnel was immersed into position, sand flow foundation underneath, and then backfilled. So the conclusions you could draw from all the innovations that were being realized in the last 2 decades. It has increased the possibilities of the use of immersed tunnels for long sea straits, for difficult ground conditions, but also for specific project conditions. And quite important, in which environmental issues can also be addressed properly. Thank you for your attention.